Evening. I'm Professor Jacqueline Collier. I'm Dean of Social Sciences here, and I would like to offer a warm welcome to you all, to colleagues, students, friends of the university. And it's wonderful to see such a good turnout for such an interesting talk. I'd just like to let you know that we are streaming the talk live, so if you ask any questions, you may well be on there, and we're recording it for a podcast, so just to let you all know that is happening. So I'm delighted to introduce you to the inaugural lecture of Professor Larissa Samuelson from UEA School of Psychology. So Larissa undertook her undergraduate degree at Indiana University, receiving her Bachelor of Science honours in 1993. She then undertook a joint PhD with Psychology and Cognitive Science at Indiana University, completing her doctorate in the year 2000. Larissa joined us here in UEA in 2015 after building an exceptionally successful career at the University of Iowa, where she worked from 2000 to 2015. There, she took a leading role in the Delta Center, which is an interdisciplinary center for the study of learning and development. And Larissa still has an affiliate of the center still. In 2010, Larissa's work was recognized by the American Psychological Association for getting a Distinguished Scientific Award for her early career contribution to psychology in the area of developmental psychology. Larissa is very unusual in that she has had continuous funding from the National Institute of Health since 2004, a very great achievement. Her research focuses on the fascinating area of language acquisition and the processes of cognitive development in children. More specifically, her work explores early word and category learning, incorporating neural network and dynamic neural field models. Her highly cited research has been published in a range of leading journals, such as Psychological Review and the Journal of Experimental Child Psychology. Larissa has presented her work extensively at international conferences across the globe, US, Canada, Germany, Norway, and of course, the UK. Larissa's research has also achieved considerable media coverage, and her work in the influence of seating context, i.e. where the children are sitting, on infants' learning of names for non-solid substances was widely covered by the North American press, including the New York Times, as well as across the globe in other international media. In her lecture this evening, Larissa will introduce us to the world of developmental science, using examples from the study of early word learning in children. She will explain how children can come to be smart word learners and how the process of learning changes over time. And then finally, she will give us some examples of how the theories explored in her research can have implications for developing interventions when problems in word learning occurs. So please join me now in welcoming Professor Larissa Samuelson to give her inaugural lecture.
Well, thank you all for coming tonight. It's a very wonderful introduction. Very much appreciate it. I need to start actually by making a change. I'm actually going to change my title. Turned out that Bowie is a wonderful musician, nice inspiration for a title, but not the best muse for a talk on early word learning. So I let the children guide me instead, and I'm going to switch it to an amazing developmental system, how learning words creates smart word learning. I also want to start by thanking a number of people who make my work possible. A number of collaborators, John Spencer, who is the other PI in the Developmental Dynamics Lab here at UEA, Sammy Peroni, a former postdoc who worked on a lot of the modeling work I'll show you today, along with Lynn Perry, who worked on some of the other modeling work, and Linda Smith, my former graduate mentor and continuing collaborator. And then other graduate students, former and current. Jessica Horst is now at the University of Sussex, actually, and Sarah is recently employed, as well as Megan and Laura, who are still with me. Also, I have to, of course, thank the parents and children who make my research possible. They come into the laboratory, put up with my silly studies, and I very much appreciate it. A number of undergraduate members of the Language and Category Development Lab back in Iowa, and as Jacqueline said, the National Institutes of Health in the US for the funding. So, numerous research papers in the field of language development, a few of which I've written myself, start something like this. Children are amazing word learners. From the time they say their first word at 1 year of age to the time they are 3, they can add as many as 680 words to their productive vocabulary. Furthermore, after hearing a single instance named one time, they can generalize that name to novel category members in ways that seem right to adults. And these amazing abilities are not just known in the field and to parents and to carers, but also inform arguments about the nature of intelligence itself. So on a recent trip, I found this article in the In-Flight magazine. It's about developments in artificial intelligence using deep learning algorithms and the details of recent work in the area showing that computers can now teach themselves how to play games like Go and beat humans in chess. These are long-standing benchmarks, and so they're showing quite a lot of progress in the field. The article continues, however, to say that these new machines will not likely be our destruction because they can't do what toddlers can do. A human toddler can learn the name of a new animal after seeing an image once or twice. Deep learning engines need to be trained with billions of images to recognize something as simple as a figure in a photograph. That's all well and good, except it's not actually true. Children don't learn words in a single trial. In a simple laboratory task where a single object, like this novel object here, is presented alongside two familiar objects, the shoe and the dog, if you ask the child to get the yak, they will very smartly pick the object they don't know a name for. However, if you take a 5-minute break to color before doing a retention task, what you'll find is that children don't retain the name of that novel object. So they'll be actually at chance during the retention trial. Now, I don't present these data as a warning that the future of Terminators, the Matrix, or sentient gunslingers is closer than developers of AI think, but rather because they point to problems in the way the field of language development has thought about what children have to do. This is best illustrated by another common trope in the developmental literature, Quine's problem. Now, Quine, back in the 60s, was actually a philosopher, and he was interested in how you acquire new information, particularly in the case when you don't have a lot of starting points to go from. He presented his problem in terms of an anthropologist studying a tribe whose language he didn't know. In the developmental science literature, it's often presented something like this. Here's the common environment for a young toddler, a very busy and decorated preschool classroom or nursery classroom. So there's lots of very interesting things in this room, from toys that you can play with, to pictures on the wall, colors everywhere, right? Now, for a child who doesn't know a lot of words, suppose mom says bead. How is a child to know what this new word refers to if you don't already know some words? It could be this table here in the front. It could be this interesting thing here on the wall. It could be any of these toys that you get out and bang around and play with, or it could be this object over here, okay? Now, I've already told you that children are amazing word learners, so somehow they solve this very difficult problem. And the way the field has kind of posed that they do this is by putting a lot of very important and smart information in their head. So maybe they come to the task of word learning already knowing how categories are organized and how words are applied to those categories. Or maybe they come to the task of word learning very early, having ideas about the kinds of things people talk to and how they name those things, or what those people are talking about when they're naming objects. Okay? The issue is that I don't think this is the case. I think the problem presented to children does not look like this. They're not on the outside looking in, but rather, children and their parents are in space, and they share that space. So children are actively exploring and eliciting names from their carers in a shared communicative context. In this way, then, word learning is extended in space. Furthermore, this process is ongoing with movement in that space and multiple naming instances over time. So word learning is also extended in time. This is a developmental systems view of word learning. And tonight, what I'd like to do is present two lines of data that support this view. One reveals a surprising source of support for early word learning. The other highlights the extended nature of the word learning process. The two lines of work will fit together in being critical milestones in the child's acquisition of a new word. So the first milestone I've already illustrated, that's finding a referent in the moment. This is important because this is the in-the-moment behavior which is critical for engaging in communication, for responding to parents' requests and things like that. But to really know a word, we have to go beyond being in the moment. We need to generalize. This is the second milestone in the child's acquisition of a word, applying it to a new instance. This is where the true power of words and language really lies, in going beyond individual instances or moments to categories, abstractions, and novel situations. Okay. So to begin, when we study reference selection in the laboratory, we greatly simplify the problem presented to children. We might present only a couple objects, for example, but we'll make it difficult by using novel objects the children don't know anything about. And we'll use novel words that they don't know. We'll also make it difficult sometimes by not putting those two things together in time. This is illustrated in a seminal study by Baldwin, who asked whether 18 to 20-month-old children could map a name to a novel object when those things were not presented together in time. So what Baldwin did was present novel objects to children. She was actually seated across the table from the children, and she would present them one at a time. So for instance, let me see if I can take my clicker and go over here. We've got a couple novel objects to give you a feel, right? So what she would actually do is present an object. You get to play with it for a little bit, and then she'll take that away, and then she'll present another object, take that one away, and actually repeat that a couple times. So this is so the child has some idea of what these are, and they're not completely novel. They're not just going to grab one in the end because they think it's the most interesting because they've never seen it, right? And then what she did is she put the objects in buckets so the child couldn't see them. She got the child's attention. She looked into one of those buckets, and she said, "Modi, Modi, there's a Modi in there." Then to further separate the object from the name, she actually presented the other object from the other bucket for the child to play with again. Okay? Take it back, and then let the child see the object that had been in the bucket. Take that back. And then to ask the child which one of the objects the word went with, she'll put two together and say, "Get the Modi." All right? So that's what that looks like over time. Okay? Now these 18 to 20-month-old children did very well. In fact, 67% of them selected the object that had been in the bucket Baldwin looked into and named in her study. Now remember, she's interested in how children can use information about referential intent to study, to solve this difficult problem. And she thought probably what was going on in the child's head was something like this. The speaker intends to label the bucket on the left, the object in the bucket on the left. Object A is in the bucket on the left. Object B is in the bucket on the right. Therefore, A is the Modi. We looked at this and we had another thought. It's true Baldwin made the task hard by separating the name and the site of the object in time. But she might have actually made it easy by always keeping the objects on the same side of the table. She kept space consistent. So our proposal is that this is about objects in space and time. So if the key to children's success is the association between an object and its recent location in space, we can test this because children should fail to link the name to the object when that association is weakened. So we ran a study in which we replicated Baldwin's task in one condition. So the objects were presented on two separate sides of the table. They were placed in the buckets. We looked into one of the buckets. We provided a name. We represented the object from the unnamed bucket and then the object from the named bucket, presented both in the center, and asked the child to get the Modi. In our switch condition, however, we manipulated the spatial locations of the objects. So you can see here that on these familiarization trials, we put the objects in the opposite sides, on the opposite sides of the table. We then replicated the rest of Baldwin's task. So importantly, the referential cues during the naming event are strong and they're identical across the two experiments. So if children are selecting based on referential intent, they should select the object that was in the labeled bucket in both conditions. However, if memories for where objects were in space matter, children should be equally likely to select either object in the switch condition because the objects were both in that space. So in this experiment, much like the other experiments I'll tell you about in this first part of the talk, we ran 24 children between 17 and 18 months of age. Half were in the switch condition, half were in the no switch. We had 8 test trials with 2 different sets of objects, and of course we counterbalanced the sides, so switched which side of the table the objects were on. We changed which label was used with each kind of object, etc. Now remember, these are 18 to 20-month-old children, so they're very young. That means I can't just give them a set of instructions to tell them what the task is about. So we also include filler trials. These will be trials where we use objects we know the child knows the name of. So maybe a book and a car. We present both of those and ask the child to get the car as a way of letting them know what the task is and to check that they understand what they're supposed to be doing. In this and all other studies I'll tell you about, the children performed better than 80% on all of these filler trials. Okay, so here are our results in the no switch condition. As in Baldwin's task, 73% of the children picked the object that was in the named bucket. It's actually slightly higher than her results, but it compares quite well. In contrast, in the switch condition, only 46% of the trials do children pick the object that was in the named bucket. So even though the object was not visible when the name was said, Now remember, when Baldwin designed her task, the buckets were particularly interesting for her because she's trying to create a referential naming event, looking into the object and naming something, okay? So even though the object was not visible when the name was said, she does provide something there for the children to be looking at and thinking about. Okay, but we wondered whether the bucket was actually even necessary. So we ran another condition, and this time we removed the bucket. So during the naming event, we simply pointed to a space on the table that was empty, and we said the name. Now I want to give you a little feel for this. I give you a feel for Baldwin's, but this is an interesting case, right? So you're going to get to familiarize yourself with this object, and then with this one, and you get to play with it and everything. Do it again, right? Do it again, so you know what these things are. And then I'm going to look right in the child's eyes, and I'm going to say, oh, Modi, Modi, Modi. Nothing's there. And I'm going to take this object. You can play with that again. Take that object. You can play with that. And now I'll take both of them, put them here, and say, get the Modi. All right? A little bit weird. Strange women in labs wielding funny objects. However, children do just fine. Children selected the object that had been on the side we pointed to 72% of the time, okay? Not weird for them. But how do they do it? Well, we know that the brain encodes objects in terms of what features have been seen where. And we also know that cueing a location in space can activate those memories. So what I think happened was that when we pointed to the empty space on the table, that made the children remember what they had seen in that location. So the remembered object is actually in their head at the point the name is said. And that's how they put those two things together. Now, I can't peek inside the head of an 18-month-old to see if this is right. Instead, what my colleagues and I do is we make a computer model that instantiates our theory to test it. So this is our dynamic field model of word learning. As I said, we're going to use these models to test our theories. So what we do is make sure that the model includes all the things that we think are important. So in this case, what we have are objects, like these, represented in terms of their features, their shape, and their color. Okay? So what we're looking at here is the binocular that's on, let's say, the right side of the table. And here's the binocular shape, and here's the binocular color, and here is the spring color and the spring shape. So the model is representing the object in terms of its features, and it's holding those features together by their shared space. Okay? The other thing that's clearly important in this task is words and labels. So we'll have a field that represents labels, so different kinds of words, and we'll associate those labels with features of objects like their shape and their color. And there'll be two more fields in this model. These will be long-term memory fields where we can actually have the model have a vocabulary like young children do. So in these fields, what these dots represent would be maybe, let's say this is the label for cow, and so this might be cow shape, and this over here would be cow color. And that would be the child's memory for that learned object name. Okay? So I think it's actually a little bit easier to get a sense for this if I actually show you the model doing our task. So that's what we'll do. So at the beginning, what we'll do is we'll present the model with the binoculars, and what you're going to see is a peak of activation at that spatial location that represents the shape and the color of the binoculars. So there they are, and there they are. And what you also saw was that these fields are coupled across these shared dimensions of shape and color, so there were ridges of activation that come down here, even though there are no labels set at that point. Okay? We can see that again if we look at the next familiarization trial. So here we're going to present the spring, shape, and color, and you can see the activation going down into these fields as well. Okay? So we do those same familiarization trials with the model. It gets to get familiar with the objects that it's going to be playing with. And then we do the critical pointing event. Now, the pointing event, there's no particular shape or color because there's no object present. It's an empty tabletop. It's going to get a label, but this is a new label, so that label is not associated with any particular shape or color. But watch what happens when the activation hits the memories for what it's seen before. So you'll see this ridge of activation come in, here, and here. And then it hits memories for the shapes and the colors that it's seen before, and these get transmitted into the label fields, and it links the label Modi with this shape and that color. Okay. Of course, then we need to test how well the model did that, so we're going to present our test. And in the test, remember the objects are moved to a new location in the center of the table. So now the model has the challenge of picking an object, and it can't just be the representation it had from those objects before because they're in new locations. So it'll get the word. That will come in here. It intersects the memory for the shape and color of that object, and then it selects one of the two objects. I'll do that again because I think it's fun. Okay. So when we're doing the modeling of our experiments, we actually simulate all 8 steps in all the versions of the studies that I'll show you. We run actually 100 simulations per task and 4 complete runs to verify convergence. So we know that what we're looking at in our results are replicable within the model. Now there are no changes to any of the parameters for any of the experiments I'm going to show you today. So the same model captures all the data. Remember that in Baldwin's task and in our replication, children select the object from the named bucket with high precision when there's no switch and when we just point, but if we mess up the spatial locations, they fall to chance. The model shows the same results. So in the no switch condition, it selects the object linked via space, but in the switch condition, it falls to chance. And in the experiment 2, where we just point and there's no bucket or anything, it still selects that object. So the model supports the hypothesis that memories of what objects have been seen where can be used to link object names link names to objects. But how strong is space? We know that even 13-month-old children, if you hold up an object or gesture to it definitively and say, pointer, pointer, they will link that name to that object and be able to retain it, okay? This is extensive definition. You've got everything together at once, okay? What we want to know is whether consistent association of an object and a location can override other bases for linking a name to that object. And so what we did was a condition where we had that ostensive definition, the spring was on the table, and we named it. And we contrasted that to a condition where prior to the naming event, we had put another object in that spatial location. So the spatial location is associated with the binoculars, but the spring is what's sitting there in front of your face when I name it. Pitting space versus time. What children do in the control condition, as I said, they're very good at linking a name to an object with ostensive definition. 76% of the time, they chose the object that was there when the name was said. However, in the space versus time condition, that falls to 40%. So only 40% of the time do they choose the object that was there when the name was said, which means 60% of the time, they're linking the name with the remembered object that's no longer there. The model captures those results as well. So, would any other binding agent work? Is there any other cue that children can use besides space to link names to objects? Well, to test that, we replicated our study one more time, this time using color. So we presented all the objects in the center of the table on different colored plates. And then when it was time for the naming event, we pulled out one of the plates, we pointed to it, and we named it. We represented the objects, and then we did the same test we've done in all the other conditions. In this case, children only picked the object that had been on the plate that was the color we named 47% of the time. However, if we give them all the objects and the plates and ask them to put them back together, which one goes on which colored plate, 70% of the time they can get that right. So they do actually remember which object went with which color. They just don't use that as a way to get names mapped to objects. The model, not surprisingly, also is a chance for this condition. So here are the data from all the experiments and simulations I've shown you so far, right? The black bars are the children and the white bars are the model, and as you can see, the model captures the children's data quite well. These child data and simulations demonstrate that children's behavior in this task is really not about hidden objects or complex inference processes. It's about associations between objects and locations. Space is actually special in facilitating binding. But of course, I made my model that way, right? The spatially grounded processes seen in these experiments and model reflected in the everyday environments that children learn language in. And you think about it, right? Multiple objects are in view all the time, right? In that complex scene with the nursery environment, there were lots of things that could be named. And those things can move around. But spatial consistency could still help. And we actually thought that was the case because my son Alec, long ago, used to use space to refer. So here's Alec having lunch in his high chair. And as you can see, I don't know if you can make it out, he's eating bananas, which was the favorite food at this particular point. After he ate all those bananas, when he wanted more, he pointed to the spatial location to request more bananas. Alec used space to refer. My muse. Okay, so to test this idea, we didn't actually put children in the high chair in this study. Instead, we brought parents and children into the laboratory, and we asked the parents to teach their 13 to 15-month-olds names for objects. We coded the spatial position of the objects throughout the study, although we didn't, of course, tell the parents anything about what we were interested in. We had an experimenter test children's learning of the word so that it would be the same across all the children. And that was done by putting two objects on the table and then asking the child to get one by name. So our question here is, do parents naturally spatially segregate objects, and does it matter for word learning? To give you a feel for what the data would look like, here is a bit of the coding for one parent. I know it's really, really small, but this is actually the left hand, and then this is the left table, right hand, right table for that parent. The bars represent the objects and their location over time. So we start the objects both on the right side of the table. The white bars are the binoculars, the black bars are the spring, and these hash marks are when mom actually named things. And as you can see in this particular case, this parent started with everything on the one side, but she quickly switched so the objects were on two different sides of the table. And she kept that consistent throughout. Not all parents did that, however. So here's another parent-child dyad. You can see we start with the objects in the same place. This mom keeps both objects on one side of the table and then switches to the other side later. Okay? So overall, there was a good bit of variability. For instance, the range in which parents kept objects in two hands, the likelihood of that, ranged from a third of the time to all of the time. So some parents did it not very often, some parents did it all the time. The consistency of that ranged from about half the time to 86% of the time. And interestingly, that was strongly correlated with word learning. So here we're looking at the proportion of time in which parents kept objects in the same spatial location throughout the study, and this is their child's correct performance on that word learning task. And as you can see, parents who kept things more in the same location had children who learned more words. Now, this was not correlated with age, the number of times the mom named anything, or the total time holding. And interestingly, children were not consistent in the way they handled these objects. So, space supports word learning. Words occur in time, and their reference occur in space. And importantly, we share space, especially in early communication. Space helps us organize where we look, and it helps us figure out what we're selecting. We encode spatial information in memory, and we can use space to activate those memories. This enables the binding or the linking of words and objects and allows things in the just previous past to be brought to bear in the present. So, space supports word learning. So far, I've shown you that thinking about word learning as a system reveals a surprising source of support for one of the first milestones in the child's acquisition of a word, reference selection. Now I want to turn to that second milestone, generalization. This is a powerful ability to move out of one moment and into future moments, extending meanings to new instances. And children are actually also quite amazing at this. So here's how we test this in the laboratory with a novel noun generalization task. We present the child with a novel solid object, like this one, maybe made out of wood, and then we'll present them with a couple test objects. This one is also made out of wood, but you can see it's a very different shape. And here's one that's the same shape as the one we named, but it's made out of a different material. I'm trying to depict wire here, okay? So we'll look at this and we'll say, this is a whiff. And then we'll ask the child to get their whiff. And what we find is from about 24 months of age on, children will select the object that is the same shape as the one we named. Okay. Turns out adults will do this as well. So this could be a smart way to learn words, but only if you need to learn names for solid things in categories that are organized by similarity and shape. So this will be helpful if you need to learn a lot of names for solid objects in categories organized by shape. And that means we need to know what kind of words young children learn. If you think about it, you know they learn some things that probably fit like this. So they learn cup and bottle and spoon and car. And these are things for solid things in shape-based categories, right? Cars have a kind of prototypical shape, as do cups and spoons. But they also learn names for material categories. So milk, juice, water, and jam. Right? Those things do not keep a consistent shape. They take the shape of their container, right? But they're made out of particular stuff. And they learn some words that might be a bit confusing. So pretzel, which has a canonical shape, but it's a particular kind of material, right? And bubble, which is non-solid, but bubbles have a canonical shape. So what kind of words do young children learn? To find out, we took a list of the first 312 nouns that children typically learn before 30 months of age, and we asked adults to make some judgments. We had 13 adult judges, and we had them gave them examples of all the nouns on the list and had them think of examples. So crayon is one of the words that children, at least learning American English, learn before 30 months of age. We asked adults to think of crayons and then think, are things named by this noun similar in shape? And just say yes or no. Similar material, yes or no. Solid or non-solid. Then we took all those and we used them to classify each noun. So a noun was classified as having a particular property if 85% of the judges agreed. So these are what the statistics of the early noun vocabulary look like. This square will represent the 312 nouns typically learned by 30 months of age. And this circle then is the proportion of those nouns that are names for solid objects, quite a lot. This circle is the proportion of nouns that are names for categories adults think are well organized by similarity and shape. And as you can see, there are a lot, okay? So there are lots of names for solid things in shape-based categories for young children to learn before 30 months of age. Just as a comparison, there are many fewer names for non-solids or names for material things or non-solids in material-based categories. So it looks like children have to learn words that fit a shape bias, but we don't know which way it goes. It could be that you know that things should be grouped into categories based on shape, and that helps you learn a lot of words. However, it could also be that you learn a lot of names for solid shape-based categories, and then you figure out that's what you should do when you come into a strange laboratory and a woman's showing you novel objects you've never seen before and giving you weird words you've never heard before. So, how do we test the developmental order? Well, what we did is bring 58 children between 17 and 33 months of age into the laboratory, and we collected two measures, their productive noun vocabulary and novel noun generalization with both solid objects and non-solid substances. Here are the data. Now, we used a two-item task, forced choice task. That means that they were picking between a shape match and a material match. If they're above 50%, that means they're going with shape. If they're below, they're going with material. And we're organizing the data here in terms of the number of words in this productive vocabulary. And what you can see is that it's not until after children have a number of nouns in their productive vocabulary that they start systematically generalizing names by shape. And in the range that we tested, children were always at chance for non-solids, just as a comparison. So it looks like the developmental order is this. The noun vocabulary actually teaches children to generalize nouns by similarity and shape. So that's our hypothesis. We can test that by asking whether teaching names for solid plus shape categories creates an early shape bias. If we know where this is coming from, if we know the right origin, we might be able to move it around. So what we did in the third experiment was a training study. We brought in 30 children between 15 and 21 months of age. These children were too young to demonstrate a shape bias on the novel noun generalization task. And we ran them in one of three conditions, either a shape nouns condition, a material nouns condition, or a no training condition. And we collected two measures, novel noun generalization and productive vocabulary as outcome measures. Now our training was such that children came into the laboratory for one visit a week for 9 weeks in a row. We taught them the names of 12 real nouns that are typically not learned until after 26 months of age. And we did this in a naturalistic kind of play setting. So we'd have multiple exemplars of the category, and we would play with them, and the word would get said lots and lots, but we weren't actually trying to point out what was organizing the categories at all. Just to give you some examples, the shape nouns that we taught were things like bucket, pear, and ladder, and the material nouns would be lotion, jello, and sand. Now, our no training children also visited the laboratory every week for 9 weeks, but they didn't get any noun training. And they were tested in the exact same way. Here are the data. So again, we're looking at a two-item forced choice task, right? And above 50% means that children were attending to shape. What you can see is with both solid and non-solid test items, children who received training with lots of nouns that were categories of shape-based categories and solid things, they generalized by shape at the end of training at week 9, and they overgeneralized this actually to non-solid substances. In contrast, children who were taught names for non-solids in categories well organized by similarity and material didn't demonstrate a shape bias, or actually a material bias. And likewise, children in the no training condition also did not get a bias. This is exactly what we'd expect because, again, these children are fairly young. So, This gives us a good reason to believe we know the origin of the shape bias, because we can get children who do not yet generalize names for solid objects by shape to demonstrate a precocious bias by teaching them words. So, we can actually teach children how to attend to shape. But this study had an even more impressive result. Recall that our second measure was children's productive vocabulary. So when we brought the children into the laboratory, it wasn't completely random assignment. We made sure children started all with the same number of nouns in their productive vocabulary. And then we tracked them over the course of the study. So at week 1, as you can see, children all had, across conditions, the same number of words in their productive vocabulary. And across the training, they continued to learn words at about equal rates. But after that 9th week, when these guys have acquired a shape bias, something happens. We track their vocabulary development after, and you can see these children go on to show an acceleration in their vocabulary development relative to children who didn't receive training or children who received names for non-solids in material-based categories. So, children learn how to learn words. These studies support the proposal that this is the process of early word learning. They learn many names for solid things and categories organized by similarity and shape. Learning some of these teaches them what to attend to when learning new names, and this actually speeds up word learning. Okay. So far tonight, I've shown you that space is a surprising source of support for young children's amazing reference selection abilities. And I've shown you that word learning is extended in time as the statistical regularities among the words children learn teach them how to learn new words. Both of these insights come from thinking from a developmental systems perspective. I think this is critical, and it's a change in the way we think about early development because it provides a deeper understanding of the origins of change. And in so doing, I think it actually can also pave the way for better interventions. So in the last part of my talk, I'd like to provide some pointers in that direction by combining the two components of what I've shown you. So in particular, in making the argument that space supports early word learning, I presented a computational model. And now in making the point that children learn to learn words, I highlighted the statistical regularities in the early noun vocabulary. Now I want to present is my most recent work where we are closing the loop by asking whether our model taught the statistics of the early noun vocabulary can learn how to learn more words. And then I want to point to my future work using this model to change development. So these are simulations of learning to learn words, and in particular learning a shape bias. In these simulations, we take the same model I showed you before. We actually use 5 individual instantiations of that model, and they're each taught a unique 129 word vocabulary. Now, it's a smaller vocabulary than what children get. It's not the 312 nouns. That's just because we're going to do this over a long time period, and that's to cut down the processing time. We'll use a gradual learning algorithm, so it'll be presented with individual instances and allowed to form an association between a word and the properties of the objects, and it'll get multiple exemplars of each noun, much like children do. The properties of the particular nouns that it'll be taught will be the same vocabulary statistics that I've shown you that children learn, okay? And here's the actual breakdown in that 129 word vocabulary. Here are the results. So we're looking at the model's performance in that same novel noun generalization task, same kind of idea, where above 50% is shape, and below 50% means you're picking by material. And we have 5 different models with the mean performance across the models in this dark black line, okay? Now there are 2 things to note here. First, at the level of the mean data, the model does develop a shape bias here at week 7. So learning this vocabulary statistics is enough to get the model to show a shape bias. Second, because we run each of the models 200 times, these lines here are robust trajectories of development across the model's acquisition of its vocabulary. And what they show are actual individual differences in the word learning and biases demonstrated by the model. These differences, like individual differences in children, will be related to the specific composition of the model's vocabulary across development. So we took our model, a model that was designed to examine children's reference selection, and we taught it a vocabulary like what children learn, and it developed the same bias that they did. Moreover, it showed individual trajectories of development. And this is important because not all children show a shape bias. In particular, children who have language learning difficulties do not show the same bias as typical language learners. Oops, I keep forgetting to. So the question I want to ask in my, late talkers, for instance, these are children typically defined as children whose vocabulary is below the 25th percentile for age and gender, do not demonstrate a shape bias. Likewise, preschoolers with specific language impairment demonstrate a reduced bias. Okay, so these are children who show no other cognitive problems but have trouble with language, as well as children on the autism spectrum who do not demonstrate a shape bias either. The question I want to ask in my future work is whether we can use our model as a clinical tool to try to change these developmental trajectories. In particular, can we capture data from individual children in our model and then test possible training regimes on those models to find the best possible intervention for a particular child? To do that, though, I first need to know that I can change the behavior in the model in systematic ways with intervention. So as a first step in that direction, we've modeled some of the data from another of our shape bias studies. Recall that I showed you we could change the trajectory of development in groups of children by teaching names for solid objects in categories well organized by similarity and shape. So we are now simulating those training studies. What we do in that simulation is the same kind of overall learning, but we add a few extra words within the first 2 rounds of word learning for the model. We then test the vocabulary at the end of each round of word learning the model does. And we also test it in novel noun generalization. And in our vocabulary test, I should say, we don't include those extra training words in the tests. So this is what we found in terms of novel noun generalization. The purple line is now the models with the special training, and the black line is the mean data I showed you before from the standard training. And what you can see is the model does develop a precocious shape bias here at week 3. In addition, the model also shows an acceleration in vocabulary development. So our model, like children, can learn to learn words. And I think this provides the basis for creating interventions for children who are not showing the same proclivity with early word learning. Our model captures individual trajectories of shape bias development, and it shows how the timing of that bias can be changed with training. In particular, we can get accelerations in vocabulary development. So the next question is, can we create individual models and test interventions to create custom training for children falling behind? Now, I'm not doing that yet, but the plan would be for an individual child who is a late talker, for instance. Could we measure that child's vocabulary and their generalization biases, and then model the trajectory of that child's vocabulary development? Change the parameters in our model to capture the specific findings of that child. Then, can we take the model and give it training with vocabularies that have different properties to see which creates a shape bias and accelerates word learning? So what's the best intervention for that particular child given their statistics and the way they think about learning words? And then can we intervene with the child to teach them the vocabulary that shows the most promise for enhancing word learning? So rather than an intervention program with every child getting the same set of words, we'd be tailoring the intervention to the individual child. And we can do this because we understand word learning as an amazing developmental system. So to conclude, I started today by presenting some problems with the way we've thought about children's amazing word learning abilities. I've shown you that children actually don't learn words in a single trial, and they don't use lots of fancy knowledge about how things are named in doing that. Instead, they're embedded in a word learning system that is extended in space and time. I've shown you that children learn how to learn words, and I've used a computer model of the brain to capture this process. And I've also been able to capture with that model individual differences in these learning trajectories. And now I've given you the first peek into our efforts to start using this model to create intervention tools, helping children who are slower or behind in word learning to become amazing word learners. Thank you.
I'd like to thank you very much on behalf of us all here and those people who are watching live. And for the people in the lecture theatre, I'd like to invite you to join us outside for some refreshments, and I think Larissa will be happy to chat people through for those who are shy and would like to ask a question in person. So thank you very much indeed.